Start off with this cartoon that I don't think is particularly funny, but it is perhaps apt in that despite our weather here in western Washington and west of the Cascades the last few years in general and the last couple of days in particular, there are some real competition for water in the region, and we have to be mindful of that. What I'm going to do today is very briefly go through just a historical perspective on what we've seen in terms of the kind of year-to-year and decade-to-decade climate variability with a focus on precipitation. Following up on what Dennis Hartman and Lou Ann Thompson presented earlier this morning, kind of the anticipated changes in this very key attribute of our system. Obviously, we're talking about a very diverse place in terms of precipitation, from the deserts of the parts of the Columbia Basin to the rainforests in the west. Let's cut to one of the chases. Are we seeing changes in precipitation around here? Here's a big picture, the Northwest, which is Oregon, Washington, Idaho. There's different ways you could define it. This is the annual amounts of precipitation averaged over those three states. And the screaming message is, see year-to-year variability, of course. You see periods of lesser and greater amount. When you fit a line to these to this data, it goes slightly up. But I think you'd be hard-pressed to claim that there's any sort of systematic, meaningful change in the historical record, at least in this very broad sense. Snowpack is a big deal around here. And I imagine many of you in the room here recall the snowpack gate. And just one thing I'd like to ask, do we always have to use gate at the end of any sort of controversy? And how long are we going to have to endure that? But anyway, there was some dispute about whether there was, whether our snowpack was declining, the water in the bank that we need for the summer. And there was, essentially, it kind of depends on what sort of period you look over. And if you pick a particular interval here from the 1950 to the late 90s, it actually had quite a bit of a decline. Recently, we've been blessed with some abundant snowpacks, and so it's gone up. Over the entire record, it's declined slightly. But again, the screaming message so far in what we're seeing in the climate is more variability than any systematic change so far. Okay. And another kind of thing to worth pointing out is it's, everything's local, right? And for somebody who's maybe living in, one part of the state versus another part of the state, if you actually look at a particular month, and I just picked these just for the sake of picking the individual months, our precipitation trends over a period from the very end of the 19th century into the present is kind of summarized here with blue dots, meaning increases in temperature. Again, just in the month of April. The size of the dot is relative to how large that increase is, with red dots being decreases in precipitation. And the message here is, wow, it's almost unanimous. Everybody's getting wetter in spring over this century-long interval. But it's a much different message here in fall, where it kind of depends where you are. Some are going down, some going up. And so it's one size doesn't fit all. Okay, going right into the future here. In the kind of little synopsis of this talk that was assigned to me, there was something I mentioned about temperature also. And here to kind of get down, even though I'm going to focus on precipitation, temperature is an important part of our climate, of course, and to kind of show you some of the results from our climate projections on the local scale. Here is the, based on an ensemble of model results, what the forecasts are of in the middle of winter of the temperature from the more or less the present climate, the 1990s, to the middle of the 21st century. The increases in degrees Fahrenheit. You see this, perhaps it doesn't look so alarming. You might even think, well, shoot, that's pretty good. You don't have to heat the house as much. Let's go to the end of the century, and this is Dante's version of Washington State. Same color scale, and here, if this actually happens, this is going to be a different place. And this is our best estimate from a variety of models with sort of regional models embedded in them to show some of the details in the terrain that kind of come out in these forecasts. And so this is a big deal. This is one forecast. This is a model mean representation of what's going to happen, but we don't know exactly. The different models are showing different results. We don't know how much carbon dioxide we're going to have in the atmosphere, and so you have to kind of anticipate there's going to be a range of outcomes. And here, this again is for our Pacific Northwest region, and by the end of the century, and this is for the year as a whole, that we're looking, we might luck out and have just a few degrees Fahrenheit, but it could be quite a bit more. And notice kind of the relative magnitude of the spread here. Check out the precipitation here at the bottom, what the models are saying there, and in particular, how big a spread there is or range in those model predictions. And again, looking at an annual average, it doesn't, the models as a group aren't showing too much in the way of overall changes, but the seasonality of it is liable to change. And this is a key point, and our systems are adapted with our present kind of the seasonal weather, right? And what the models are saying is that basically the winters are going to get wetter and the summers probably are going to get drier. And here, this is for the changes in just the next decade or so are not going to be, probably going to be that large vis-a-vis the natural variability in the system. By the 2040s, that probably should start emerging. By the toward the ends of the century, it's definitely looks like there's going to be some changes. What I like about this particular plot that was actually produced by the Climate Impacts Group, and here I got to give a shout out to Laura and her group for doing this. I've stolen a lot of this stuff without any guilt whatsoever. But so anyway, the individual model forecasts are shown with these little dots here, and this is what's called kind of a box and whiskers plot to show you how what they're showing in the mean and kind of the variability among those projections. And so you can see that while, sure, as a group, there's a consensus of wetter winters and drier summers, it's not unanimous. And so that is something that we just have to keep in mind, that there is this range of possible outcomes, and we just have to be able to take that into account when we're planning for how to deal with it. Okay. Now, getting back to the snow cover, what this means, the increase in temperature means that less of the Cascades is going to be have snow. This is kind of the historical sort of April, where there's snow on April 1st with the amount of, here indicated the deeper blue means a deeper snowpack, and here the amount of red means how much of a reduction, and we see just because the freezing level is going up that there's going to be less of the cascades that's going to have snow going into the summer season when we need it. If I had to have a single plot to summarize what is the biggest threat to the environmental and economic health of the Pacific Northwest and associated with climate change, I would pick this one. Because what this shows is a time series based on kind of historical data here in blue there, 1990s for what it's worth, is how much water is in the snowpack here at a representative place in the Cascades, Stampede Pass at about 4,000 feet. Okay, it shows that we have 250 millimeters, about 10 inches of water equivalent there in the snowpack bank going into the spring and summer. And these are the forecasts based on our models of temperature and precipitation, and that include estimates of how fast it will melt and that sort of thing, that show the decline in that snowpack with time over the century, and here at the end of the century, how little water we're going to have in that snowpack. And that snowpack is what it's important to hydropower generation, agricultural water supplies, stream ecosystem health, and so forth. And so this is, I would submit, is a really big deal. And what that means, just to kind of belabor the obvious perhaps, is that whereas some of the Cascades now is kind of snow dominant, here indicated with these blue colors, and others are kind of a mix of snow and rain, that with time there's going to be less and less of the Cascades that's snowy, basically. What's this going to mean? And here I'm interested in kind of scooping what some of my colleagues are going to be saying either later today or especially tomorrow about what the implications are for various things. Here's an example for the Columbia River. I use this to kind of illustrate what some of the implications are. If the Columbia River didn't have any dams on it, because of all the snow that's in its watershed, it would have its its peak flows in the early summer. Half of the water that goes into the Columbia is from Canadian. Is in Canada, and some pretty high mountains there, and it's it's a snowy place right now. We manage it because of the dams so that we actually have more water coming out in the winter months and less in the summer than it otherwise would. Another implication of this change in the kind of snow versus rainfall properties is that we expect more wintertime floods. And here the size of the circles and how red they are refer to the magnitude of the floods that we're estimating under these different greenhouse gas scenarios in maybe the relative to the historical floods in the next decade or in a few decades. What's that? A portrait of Lincoln, right. Yeah, and that's kind of what our models are sort of like, and I just, again, I had them here, so I got to show them, right? I think our models are more like this. We're getting more into them and a little bit better representation, but still as a caveat, they are imperfect, and we can't say their projections can't be trusted explicitly. All right, that being said, we do have some capabilities to make projections on smaller scales. Here, if we give our, we have high resolution weather models for getting the details and the weather forecasts right and that sort of thing. If we give it the right large scale conditions, it can reproduce some of the actual rainfall distributions we can see in major floods. Here, there's one back in November 2006. This is what fell. This is what the model predicts if it's given this the right large-scale conditions. But again, we don't know exactly what those large-scale conditions are going to be. And so there's always going to be this range of outcomes. And that's just a fundamental thing that we're dealing with. Get back to this point that it's getting, we expect it to get wetter in the cool season, drier in the dry season. Are we seeing that yet? I just showed you before annual average precipitation. Here, let's go back just October to March. Again, you can look for yourself. I would say when you actually fit the line to it, it's exactly flat. It's not really changing. What about summer? Over the 100-year record, it's actually going up, but if you actually squint at this, perhaps you can, it looks like in the recent decades, a disproportionate number of the summers have actually been on the dry side. So maybe we're just starting to see something there. In terms of floods, this is a particular river chosen. I don't know why I chose this from previous talk, but this just shows the peak stream flow values year by year. One of the reasons I chose it is because it's got a long record, and you can see, this is the way the floods work. Recently, the floods have been larger. And so maybe we're starting to see a kind of hints of what we're anticipating to be more so in the future. Here's something I couldn't resist putting this up. It's some work I've done just the last couple of weeks, and so please indulge me. E.T. is not an adorable character from a Spielberg meeting or something. It refers to evapotranspiration. And while this whole segment is about water availability, there's also perhaps some changes due to climate in water demands. And this potential ET in particular relates to how much water is required for an irrigated region. And what we see based on direct measurements from 5 sites in the Columbia Basin is that ET in the late 80s, early 90s has gone from something like 0.26, 0.27 inches per day, whatever that means, to something higher. If you actually convert this number 100 days of summer or something, it means like 3 or 4 inches more of water is needed for those irrigated regions per summer than it was a couple of decades ago. We've had abundant snowpacks recently, and so that hasn't been a problem. But if we have a dry year and we continue to have this higher water demand, then that could be a problem. So far, our trends, the observed trends in precipitation, are small compared to the variability. There's a strong, if not overwhelming, consensus from our climate models, the best tools that we have available, that there's going to be substantial decreases in snowpack because higher temperatures. We're sure about that, but also higher flows in winter because of wetter winters, and reduced flows, at least on uncontrolled streams, because due to drier summers overall. And our models are now getting the ability to start teasing out some of this. We definitely don't have it completely figured out. And the last thing I want to leave you with is that this variability in the system on timescales of years to decades is still going to dominate for the next at least 10, 20 years. And so people are still going to say, wow, it was a wet, cold winter, so what happened to global warming? Well, that's still going to be there. And so I'll close with that one. Thanks. What's next, right? Thanks.